Okay, how do we find equilibrium concentrations? We looked at how we can calculate the equilibrium constant, but how can we find equilibrium concentrations? And this is a very useful technique or skill. There are two kinds of problems. The first one is where we know the equilibrium constant and we know all but one of the equilibrium concentrations. This is pretty straightforward. We just plug those known things into the equilibrium expression and we solve for the thing we don't know. And we'll do an example of that. More common is the second kind of problem where we have the equilibrium constant and we know what the initial concentrations are, but we don't know anything about the equilibrium concentrations. And that's where we're going to use an ICE table. So let's do the more simple problem first. Diatomic iodine decomposes at high temperature to form iodine atoms according to this reaction. In an equilibrium mixture, the concentration of I2 is 0.10 molar. What's the equilibrium concentration of I? So we need our equilibrium constant expression. So Kc is equal to the concentration of I squared, because it has a coefficient of 2, divided by the concentration of I2. And yeah, there's I's and 2's, and it's really important that we put the 2's in the right place. Yeah? Okay, so we're given the equilibrium constant. So that's 0.011. And that is going to be equal to the concentration of I squared. That's what we don't know. Divided by the concentration of I2, which we do know. Oops. Helps if you can copy the numbers down correctly. So this is a pretty straightforward equation. So let's just run through real quickly how you would solve that. So I'm going to multiply both sides by 0.1. So that's going to give me I squared is equal to 0.011 times 0.10. And then to get rid of the square, I'm going to take the square root of both sides. And so I minus is the square root of 0.011 times 0.1. 0.03317. So we'd probably report that as 0.033. And what's the unit on that? Molarity. Why do we know that? It's concentration. The brackets mean the molarity of this thing. We just always use molarity. Any questions? For this reaction, A going to 2B, Kc is 4. A reaction mixture at equilibrium contains a concentration of A that's equal to 1 molar. What's the concentration of B in the reaction mixture? We don't need a calculator for this one, but we may need to think about math a little bit. What's the equilibrium constant expression for this chemical reaction? The products squared divided by the reactant. So if Kc is 4 and A is 1, what does B have to be? 2. Any questions? Okay, so here's the other type of calculation, and this is more common, and it requires a specific procedure, a series of steps. So this reminds me of doing like empirical formulas in Chem 1A, and you had a series of steps that you needed to do. So you might want to, write these on an index card or a note on your phone or something. We're going to be doing this a lot, and so this is worth your time to remember. The first thing we're going to do is we're going to set up an ice table with initial concentrations. Then we're going to represent the changes, that middle row, in terms of X, and we consider the stoichiometry when we do this. Then we add the initial and change rows to find the equilibrium concentrations in terms of X, and then we plug those into the equilibrium expression and solve for X. And this is where the solver on a TI-36X Pro can be super useful. So here is a simple example, and then we'll do one that's a little more complicated. So here we've got A going to 2B. We're told that the equilibrium constant is 0.33, and the initial concentration of A is 1. So here's the ICE table. ICE, initial change equilibrium. The initial concentration of A is 1. We were told that. We weren't told anything about the products, so we are to assume that it's 0. Then we're going to see, well, how does A change? Well, A is one of the reactants. The reaction's going forward. It has to go down, right? So it's going to go down by some amount that we don't know. We're going to call it X. So this is going to change by negative X. How is B going to change? Well, it's going to go up, right? And we need to look at the stoichiometry here. We get 2 B's for every A that reacts. So this is going to go up by 2X. And this 2 is that 2. Okay? Then we take these rows and add them. So we've got 1 minus X and 0 plus 2X. And now we need our equilibrium constant expression. So K is equal to B squared over A. We know what the equilibrium constant is. It's 0.33. And we have things that we can represent the equilibrium concentrations with. We don't know what they are, but we can represent them. And so B is 2X. So B squared is 2X, the quantity squared. And then A is 1 minus X. Solve for X. Remember the quadratic formula? We're not going to use it. I don't like it. We don't need to do stuff like that anymore. That's lame. We have calculators, right? That can do these things for us. So if you like doing things the hard way, go ahead. You go right ahead and do that. Let's see if I can get this to work. Come on. Here, let me out of there. Okay. Trying to say it's trying to mirror to the TV at home. That's not going to work. Nothing works that far away. Okay. So this is how we're going to do that problem. Of course, now I don't have the problem to look at, so that's kind of a problem. So I'm going to do a second number solver. And I've used this before, so I've got stuff in there. I'm going to press the clear button. Pardon the Band-Aid on my finger. So to clear that out. right? So the equilibrium constant was 0.33, do I remember correctly? So this number solver here, you press second and the number solver button, and it should show you the two little boxes. Yeah. If I lose you at any point, please stop me, because this is not hard to learn how to use, but it does take a little bit of practice. But once you get it, you're going to be like, oh, this is amazing. Where has this been all of my life? Okay, so on the left side, I'm going to do 0.33. And then I'm going to move the cursor over. And I'm going to type in what it showed in the equation. Now, maybe next time I'll have my acts more together, and I'll actually be able to see the thing at the same time. That's, goals for later. But let's try to remember. Yeah, so I'm going to use the fraction button here, this guy. And then I don't have to worry about dividing by things that are multiplied or anything like that. I'm going to use parentheses and go 2, and the variable button is this guy right here. It says X, Y, Z, and some other letters. I'm going to press that. It's going to give me X. If you want other letters, you can scroll through them. I just use X because it doesn't really matter. And then the parentheses. And then I'm going to use my X squared button to square that. Looks just like what I wrote on the screen, right? Now I'm going to move the cursor down, and I'm going to put the denominator in there. I wrote parentheses on the screen, so I'm going to write them here. Sometimes you need them. Here we don't absolutely need them, but it's not going to hurt anything. So I've got 1 minus x. Close the parentheses. Can you get your calculator to do that? Everybody okay? Anybody have questions? Now I'm going to press enter, and it's giving me the last answer that I got, and I'm just going to put 0. This is where I tell the calculator what to start with. So I'm saying I want you to start with 0, because it's going to do this by iteration. And then I'm going to press enter. We don't need to do anything with that, so just press enter again. And it's not instant, but there we go. 0.2489. Bingo. Cool, huh? That's very cool. So let me show you something else, because if you remember from math, quadratic equations typically have 2 roots. There's 2 solutions. And sometimes the calculator gives you the one that's appropriate first, and sometimes it gives you the one that's not appropriate. So here it gave me one that's good. How would I know if it's not good? If it gave me a negative number. The concentration of my product is 2x. Concentrations can't be negative. How could that end up happening? Well, that could happen if you start somewhere else. I'm going to try starting with -1 here and just see what happens. There, it gave me a negative number. Negative 0.331425. That root does not work for my problem. So if you get a root that doesn't work, then you go back. Hello. I didn't say anything. Oh, my phone went to sleep. Okay, I can fix that. Ooh, that's okay. I just shared my password with the universe. Okay, I guess I'll have to change that now. So if it gives you a negative root like that and you started with 0, then go back up here and start with something else. -1, will often come at it from the other direction, or positive one, okay? But here we have our answer, coming back in a minute, yep, 0.2489. There we go. Not exactly seamless, but, not bad for an old person. Of course, now I can't, my writing's all gone. So we used the solver and we found out that x was equal to 0.2489. Is that our answer? It's part of our answer, right? So we want the equilibrium concentrations of these guys, so we need to plug x into these expressions. So the concentration of A is equal to 1 minus x. So 1 minus 0.2489. The concentration of B is equal to 2 times x. I have to pull my calculator out of here, note to self, get out a second calculator next time. 1 minus 0.2489, 0.7511, 2 times 0.2489, 0.4978. So, ridiculous number of sig figs, right? We're subtracting here. So if we're going to get picky, this answer should only have one decimal place. I think if you're going to make a mistake in sig figs, include too many. So I'm going to include one more than I think I should, and I'm going to say the concentration of A is 0.75 molar, and the concentration of B, that's going to round to 0.50 molar. Any questions? Did we get the answer right? Oh, that one isn't, yeah, that one doesn't give me an answer. Okay. So let's try one with with actual chemicals, right? N2 plus O2 goes to 2NO, and Kc is equal to 0.055. Says the reaction starts with only the product and no reactants. Find the equilibrium concentrations of all of them. So the first thing we do is make an ice table. We're going to use the chemical formula, the chemical equation as the header row. So I'll copy that down here. So that's my top row. I'm going to have a row for I, a row for C, and a row for E. And then I've got columns. I'm going to just do a double line here. And I'll just finish that guy off. Well, let's finish this off too. Oh, we might as well finish off the top too. Just make it all pretty. So this is I, this is C, and this is E. Okay? Make the ice table. Put in the information that you're given, which is going to be initial concentrations. So we have a concentration of no is 0.0100. So here is my product. So this starts out at 0.0100. And it said there were no reactants. So the concentrations of the reactants is 0. Okay? Now we're going to fill in the change line, and we're going to do this in terms of x. So if we look at this product, this reaction only has product, so it can only go to the left. You see that? So this is going to have to go down, right? How much is it going to go down? Well, we can start with minus x, and then we see, oh, well, there's a 2 here, so we're going to call that 2x. Because over here, these guys have 1s, so we want to use the coefficient with x. Right? Here's a coefficient of 1. We don't write the 1, but we understand that it's there. So that went down by 2x. This one goes up by 1x, right? Because it's got a coefficient of 1. And the oxygen will also go up 1x. Everybody with me? Now we're going to add. We're going to add the initial and change rows. 0 plus x. Ooh, this is tough stuff on a Tuesday morning. 0 plus x. Okay. And then this one, 0.0100 minus 2x. Okay? Now we're going to write the equilibrium constant expression and plug these things into it and solve for x. I'm going to do this up on the top for a change. So K here is equal to NO squared divided by N2 times O2. Now I'm going to plug things in. We know what Kc is, 0.055. What's NO? That's what's in this box. That is squared. So I'm going to write this here, 0.0100 minus x. Nope, minus 2x. The quantity squared. Divided by N2 is equal to x times O2 is equal to x. Yes? Yeah, so it seems like NO is the reactant here, right? Because it's the thing that's changing, is going away. So what's kind of tricky about equilibrium reactions is because they go in both ways, we can write the equation in both ways. If we wrote this, if we flip this around, then what we learned is we have to invert K. So this whole thing turns upside down. So we could do that, but it's a lot of extra work and ends up getting us the same place. So that's a great question. Any other questions? Would you rather see this as x times x or x squared? X squared? Okay, so I'm going to make that x squared because x times x is x squared. So now we're going to use the calculator. Let's see if I can do this maybe a little faster this time. Bring the calculator back. Okay, so I'm going to go second num solve. There's my equation still from last time. Clear, and come over here and clear. If you just need to make changes, you can do the delete button, but then if you were trying to delete all of it, it's going to take a long time. Okay, so my rate equilibrium constant, what was it again? 0.055. Okay. And then over here on the right, I've got a fraction, so I'm going to use this fraction button. And in the numerator, I have the quantity 0.01 minus 2x. Close the parentheses and make that squared. So one thing that can happen using the solver, one of its limitations is there's a limit to how many characters you can put in here. Ooh. So you notice I did not put a 0 in front of that decimal point. I did not put the trailing zeros here. So there's a lot of places where you can leave some things out that aren't going to affect the number that gets calculated. So that can help with not running out of numbers or characters. So I'm going to go down here, and I want x squared. Everybody getting that okay? Now I'm going to press enter, and I'm going to start at 0. And it's giving me 0.004475. Okay? So we found out that x was equal to 0.004475. I'll figure out how to get the work back this afternoon. So then when we look back at that ICE table, we see that the equilibrium concentration of NO was equal to 0.0100 minus 2 times x. So we can calculate that. Point 0.01 minus 2 times. And if we did this on the solver, I can press that variable button again, x, and it will pull that number back from the solver. And so this is going to give me 0.01045, and it's like, okay, well, we went plenty far there. So I'm going to call that 0.0010 molar. It's based on sig fig rules. And again, we're not going to get crazy about sig figs here. So N2 was equal to O2, and each of those was equal to x. Right? So 0.004475. How should we round that? Well, I think 0.0048 would be reasonable. We want to write down what our calculator gives us with at least 2 extra digits. Then say we're doing mastering chemistry, and we plug our answer in, and it's like, no, you need more sig figs. Okay, no problem. I'll just go back up here and pick up 1 or 2 more. It's fine. If I round this off here, and I find I need more sig figs later, then I have to do the calculation again, right? Any questions?
Just a small mistake, just for the recording. 4.
Oh, yes. Thank you. I appreciate that. I rounded the 5, the 7 up to an 8, and just skipped the other 4. Thank you for catching that. So this should be 4 or 5. okay? Questions? So here, they rounded it a little bit differently, right? So this is the same, but here they called it 0.0011. Well, where'd that come from? Honestly, I'm not sure. Because I got 10 here. 0.01 minus 2 times 0.004475. Okay, if I use this rounded number, it gives me 0.00105, which would round to 0.0011. Do we need to be concerned that this value and that value are not exactly the same? No, we don't. If a value is written correctly according to sig fig rules and precision, etc., the last digit is known to be uncertain, and so a small difference in the last digit, not a problem. Okay, let's do another one. Here, the reaction mixture is at 100 degrees C initially, and Kc is equal to 0.36 at 100 degrees C. Remember, they're going to throw temperatures in there. It's kind of like the small print, the fine print on a legal document. You actually don't need to read that, maybe. Well, my lawyer daughter-in-law would disagree with that, but we're not going to use that number in the calculation. Okay, so we don't need to worry about that one. So we've got initial concentration of this reactant, and it tells us no product. Find the equilibrium concentrations. So, ice table. N2O4 gas in equilibrium with 2NO2 gas. I'm going to have initial, change, and equilibrium. So ICE, that's why we call it an ice table. I make my ice table, and then I'm going to put my concentrations in. So here's the initial concentration of the reactant, 0.0250. And there was no product, so that's a 0. In terms of X, how is the concentration of N2O4 changing? It's going to be minus X. How's the concentration of NO2 going to change? Plus 2X. Because when one of these reacts, we make 2 of those. So this coefficient becomes the coefficient in front of the X. Then we add the first 2 rows to get the equilibrium values. So we've got 0.0250 minus X, and we have 2X. The equilibrium constant expression, NO2 squared, divided by N2O4. Plug in the numbers. 0.36. The NO2 is 2X, and that's going to be squared. And down here, 0.0250 minus X. Okay, so get your solver out and plug this in. You do need these parentheses here because the 2 is also getting squared. Or you could simplify it and put 4x squared. It's kind of up to you. So that's what I got for x. Anybody else get that? Yeah? Okay, so now we can calculate the equilibrium concentrations. So N2O4 is 0.0250 minus 0.02038. Zero point 00462, and I'd probably round that to 0.0046. And then the NO2 is equal to 2 times x .04076. And I'd probably round that to 0.41. But, you know, we could have a discussion about that. I'm just going to peek and see if I got the answers right. Okay. So they rounded it to 0.005. I kind of disagree with that, but it's okay. I'm going to go back to my solver and see what the other root was on that one.
Like putting x equal -1.
Okay, so the other root was a negative number. Sometimes you get 2 positive roots. And then how do you know if it's not good? Well, let's pretend that the other root was 0.1503. That's a positive number. That should be okay, right? But if we subtract this from 0.025, we would get a negative number. So if something like that happens, you may have the wrong root, or something else might have gone wrong. It's easy to make a little mistake over here, like if you forget the parentheses. What I like is that you can go back and look at what you typed in and compare it to what you wrote down to see if you made a mistake. Any questions?
So to get the next root, we can just put x equal -1 or 1.
Yes, so to get the other root, usually it works if you start, instead of x equals 0, x equals -1, x equals 1. Sometimes you have to get a little more creative, but not usually. Oops. So let's do one more here. This is with pressures. We have our chemical reaction. We have a temperature that matches the temperature for the equilibrium constant. And it says that we have partial pressures of 0.15 for each reactant, and there's no product. So we're going to make an ice table. We're going to be making so many ice tables. I2 plus Cl2. It's not just this chapter. It's in a couple of other chapters as well. Here we don't have concentrations, we have pressures. That's okay. Both reactants have initial pressures of 0.150 atmospheres. And it says there's no product. How does the pressure of I2 change? It's going to be negative X. It has to go down. Could this possibly go up? No, because there's nothing over here to react. We will get to situations later where you've got some on both sides, and it could go either way. And that's where you can use Q to tell you what direction it's going. So that's minus X. This one's also minus X. And what's the change for this one? Plus 2X. So now I'm going to add those together. I've got 0.150 minus X, 0.150 minus X, and 2X. Kp is equal to the pressure of ICL squared divided by the pressure of I2 times the pressure of Cl2. Kp equals 81.9. In terms of X, the equilibrium pressure of ICL is 2X. We have 2X squared. And then down here, I get 0.150 minus X. And that's going to be multiplied by 0.150 minus X. So I can just call that the quantity squared. So I'm going to go back to my solver, 81.9. On the right, I'll make a fraction. I'll do 2x squared. In the bottom, 0.15 minus x is a quantity squared. So I'm getting 0.12285. There are several different error messages that the solver might give you. It might give you max iterations, which it has a limit to how many times it will iterate before it gives up. And if that happens, you need to give it a different starting point. So maybe -1 or +1. There's also a couple of other errors that'll come up, and what you need to do is you need to go back and look at your the equation that you typed in and make sure you didn't make any mistakes. So the final pressure for I2, or the equilibrium pressure, is going to be equal to the equilibrium pressure for Cl2, and that's going to be 0.150 minus 0.12285. 0.02715. I'm going to call that 0.027. And these are pressures. So these are going to be atmospheres. The partial pressure for our product is 2 times X (0.2457) call that 0.25 atmospheres. Any questions? Okay, they did 246. I did 25. It's okay. So we're going to stop here for today. We'll pick up on Thursday, and we're going to look at a simplifying approximation. We do not have to use our solvers all the time. So there are times when we can make a simplifying approximation, and it makes the algebra much, much easier. If you are not a fan of algebra, if you don't get along with algebra, use your solver for everything, right? It's amazing, and it's not cheating. This is not math class.